recurrent neural networks can be extremely effective at modeling time series, both at making predictions and at analyzing them. So we saw this example where there was a recurrent network that actually wrote out a computer program, and the program is complete in terms of syntactically complete. Every open parenthesis is closed, the variables are properly referred to, and so on. So we saw that when we want to analyze time series, then if you're interested in short-term time dependencies, so if you have some time series data of this kind, where the prediction at any point depends only on a small window of inputs in the past, then you can have iterated structures. What we meant by iterated structures is where you're iterating over the inputs and you're producing an output. So these were finite response systems. They have a short time dependence on the past, and these are basically just time delay neural networks or convolutional networks. And this sort of aligns also with our earlier perspective that convolutional neural networks are basically just scanning the input with an MLP, right? But we saw that if you want time series with long-term dependence, specifically with arbitrary dependence on the past, then it's not sufficient to have iterated structures. You want recurrent structures, things that self-refer. They're self-referential. They refer to their own values from the past. And this was one of the standard kind of structures that we saw. At each point, you compute a hidden representation of the input, and the hidden representation depends on the hidden representation computed at the previous time instant. That's how we got our self-reference, right? And these things tend to be able to refer all the way back into the past. So here, for example, something that happens here influences down this chain the output at this time instant. And we also saw that recurrent structures can do what static structures cannot. So the simple problem of trying to train a neural network that learns to add 2 n-bit numbers. Now, if you were to do this, you can do this. This is a completely static problem. There's nothing recurrent about the problem per se. I'm giving you 2 numbers. You want to add them. But if you wanted to do that using a static structure, both the size of the network and the amount of training data that you would have to provide could end up becoming exponential in the size of the input. And what you learn at the end of it is very specific to the size of the input in this particular problem. On the other hand, if I just replace that with a little recurrent structure, I get a much smaller structure, which also learns to generalize much better than the static structure itself. So here's a surprise result. By introducing self-reference, something that conceptually is a more complex structure, practically you end up with structures that learn to generalize, that could potentially learn to generalize even on problems that are solvable using static structures. And they can do so. And now this unit can be trained using far fewer examples. There are only 3 input bits, 2 output bits, a total of 32 combinations of inputs, 32 input-output combinations will completely specify everything that this unit must learn. Now, when we want to train these recurrent structures, we saw that they can be trained by minimizing the divergence between the sequence of outputs that the network produces and the sequence of desired outputs. So when the network operates on a sequence of inputs, it's going to produce some outputs. The outputs could be a single value, they could be a sequence. In the most generic instance, we will assume that the output is also a sequence. Now, there's a desired output. If you're training, you're going to be given input examples where you have the input and the desired output for that example. And the desired output also is going to be a sequence. And we must compute the divergence between the desired output and the actual output of the network. And we can now compute the gradients on this divergence. The divergence is not the divergence between instantaneous outputs and instantaneous target outputs, but over entire sequences, again, to be reiterated. And we can compute the derivative of this divergence with respect to the individual outputs and then backpropagate everything to train the parameters of the network. And so the primary topic for today and for the next couple of lectures is how do we deal with this business of trying to backpropagate divergences when the divergences themselves are kind of imprecisely defined. Well, the divergences are not imprecisely defined, but there is no clear way of assigning any component of the divergence to a specific, uniquely to a specific output. But to continue with the story so far, we saw that recurrent networks can be unstable. So you've all gone through the quiz, I assume. So you've also done your little simulations to see how these things can forget. And I could have given you the reverse problem, and you could have gone through how these things can explode. And we saw that if you have linear activations or even ReLU activations, which are basically just linear activations, for an improper setting of the weights, the outputs can just blow up. They can blow up exponentially. So it's not really for remembering anything, it's just going crazy. On the other hand, if you try to control the behavior of the network, so that the behavior doesn't, the network doesn't explode, then it has this unfortunate habit that for some activations it quickly saturates and forgets about whatever it was that initiated the response of the network. For other inputs, for other activations, it will still saturate, but it will saturate slower. So we found that the one there where the response was more reasonable was the tan-H activation as opposed to, say, sigmoids. And ReLUs, of course, have the tendency to blow up. So these have a stability issue. And we also saw that we saw a problem that's not specific to recurrent networks, but it's true for any deep network. And we already know that a recurrent network is basically a very deep network where the depth of the network is arbitrary. The depth of the network depends on the length of the input and the length of the output. So, when networks become really deep, then when you backpropagate the error, as you backpropagate it, the errors, the derivatives either tend to basically vanish, or very locally they may blow up. And so here we saw an example. This is not a recurrent network. This is just a straightforward multi-layer perceptron, 14 layers deep, where we were trying to classify MNIST data. And this is the output layer. This is the input layer. These are and the brightness and the image shows you the magnitude of the gradient for each of the parameters of the network at different depths. And what we saw was that, and this was at initialization where the gradients, you expect the gradients to be more steep. What we see is that although you see some fairly strong gradients just at the output layer, as you begin walking backwards, by the time you're out to the 10th layer, you don't really see the gradients at all. Most of them are down to very, very small insignificant values. There are a small number. Obviously, the network is responding to changes in the input. What has happened is all of the response has been pushed onto a small number of these parameters, to which now the network becomes hypersensitive. And the rest of them basically don't matter. You can modify them quite a bit, and the output is not going to change. So what we found is by the time you got from the 14th layer to the input layer, basically the gradients are all basically vanishingly small or completely gone. So we have this problem of vanishing gradients as the network becomes deeper. When you try to propagate gradients backwards, the gradients become smaller and smaller. It also depends on the activation function that you use. Now we actually saw why this must be true all the way back in lecture number 2. Now in lecture number 2, we said something about the units propagating information onto subsequent layers. Does anybody remember what we said about that? Shankai, I see some. We did say that, right? We said that if I use threshold units, if I have less than the required number of units in the input layer, no information is being passed downstream. And therefore the deeper layers cannot recover the patterns. You remember that? Right? And we said for the deeper layers to be able to recover the patterns, you want information to be pushed downstream, which means you want activations which are not thresholds, but which actually carry some information about the distance from the boundary. And the more information these activations carry, the easier the network is going to find to learn what about the patterns that it must discover. And that actually comes back over here. So what are the most informative activations in that sense? The ReLU. When you're on the positive side, it just pushes all the information through. It's only when you're on the negative side that it blocks it. Or you can have the softer version of the ReLU, which is the leaky ReLU or the ELU, and you expect those to give you decent behavior. And other activations like sigmoids or tan-Hs, they have this saturation behavior, where if you're beyond a specific distance from the boundary, information about where you are is lost. And of course, now the derivatives, you can expect the derivatives to vanish. And so this is exactly what we have over here. This is an ELU activation. This is probably the most effective activation function when it comes to pushing derivatives through. And even with an ELU activation by the 10th layer, over here, the derivatives are quite gone. We had other examples in the previous lecture where we had sigmoids and tan-Hs, and there we saw that the derivatives basically died much earlier than they did for the ELU. Questions? No. Can someone monitor Piazza for me? One of you guys. So Shalin, can you just, yeah. All right. Then we also saw the long-term dependency problem, that the network tends to forget, or in a manner that depends primarily on the weights but not on the inputs. Whereas what we really want is behavior where the memory, where the system retains memory until it no longer has to. So if you are trying to parse a C program, you want to remember that a brace was opened until it's closed, at which point the closure of the brace becomes irrelevant, right? If you're trying to analyze language, so you have something like this: Jane had a quick lunch in the bistro, then she. Now, you want the she to be triggered by the input and not the distance from Jane. Now, instead of Jane, if it had been Tom, you want the output to be a he. But you don't want the next word to be a he. You basically say that this word she, Jane had A. After had A, the word she is inappropriate. You really want the she only occurs in specific locations in the sentence, which means where it occurs depends on the input. And yet, it must refer back all the way to Jane to decide whether it must be a she or a he. So you have behavior that's triggered not only based on what is remembered, but also what the input is that triggers what the next expected input or the next output must be. And so you want input triggered response, and something like this that is not really input triggered, this is parameter triggered. And so in order to deal with this one, we introduce the notion of LSTMs, where LSTMs, although they are not strictly input triggered, if you've gone through the quiz, you will observe that at least one of the questions refer to the fact that these two tend to forget. And why is that? You can think of these, no matter how the whole entire thing has been set up at a conceptual level, you can still think of this entire thing as one very complicated function. And it's a complicated function which has parameters, and its behavior is obviously dependent on the parameters. It's just that the function is sufficiently complicated that the memory behaviors are somewhat more, how shall I say, fine-grained, or somewhat more capable of holding on to prior inputs and concepts that must be remembered than a simple tanh activation function. And this week's quiz, we hope to sort of, at least a couple of the questions will investigate the memory behavior of the LSTM. Anyway, so the LSTM addresses the point of input-dependent memory behavior. The way we set it up, the memory was, we had this CEC where the memory was not affected by parameters directly, but was indirectly affected through these additional units which analyze the input to decide what must happen to the memory, right? And when we have an LSTM-based architecture, the LSTM-based architectures are identical to standard RNN-based architectures, except that each of these boxes is now no longer just a single array of units. It's an LSTM cell with many arrays of units inside. So basically, if you had something like this, each of these boxes is going to be an array going into the page. And so the LSTM cell itself is a complex unit with many components to it. Other than that, if you think of this array of units as being replaced by an LSTM cell, then this is just a standard recurrent network where each of the green boxes gets some inputs and produces some outputs. And its behavior depends on its own values at the previous time instant, right? Now, once we agree that an LSTM is basically just another variant of a standard recurrent structure, then you can do other things like bidirectional LSTMs, where the output depends on, is produced by analyzing the input both forwards and backwards and combining inferences made from both. Now, in all of this, again, the issue really becomes how do you train the network, which is how do you define the divergence between the actual output and the target output, and in the case of both the bidirectional LSTM and the standard LSTM, how do we actually compute the outputs? So for today's lecture, I'm going to not really be spending a lot of time on bidirectional LSTMs. I'm going to be talking about unidirectional structures, but everything that we say today and tomorrow can very trivially be generalized to bidirectional structures, because as we know from the previous lectures, there's really nothing magical about bidirectional structures other than the fact that you have to see the entire input before you begin processing it. So what we are going to look at is how to train recurrent networks of different architectures. We're going to look at, yes?
For a bidirectional structure, do you use a different set of units, or is it the same set of units?
So for a bidirectional structure, this network is completely independent of this network.
Okay.
So we haven't yet put up the modified slides on the course pages, but the pseudocode should explain it to you fairly clearly, right? It's just two independent networks. Think of two completely independent networks who are pooling their outputs to produce the okay. So it's like an ensemble, except one ensemble is working one component is working forwards, the other is working backwards, right? Now, what we're going to spend the time, rest of this lecture and the next one on are network architectures. What are different kinds of network architectures and how do we train them? And specifically for today and on Friday, we're going to look at a specific kind of synchronous output, where we are looking at either time synchronous outputs. What I mean by time synchronous is the network produces outputs as it processes inputs, and for every input it's going to produce an output. Or we are going to look at order synchronous outputs. Order synchronous outputs means that the network output need not be the same length as the network input, but the order in which the outputs occur is strictly related to the order in which the inputs occur. So, and this applies only to some types of nets, and we will look at not just how to train these networks and how to make predictions and inferences with such networks. So here are the various variants of networks that we've seen in the past, recurrent networks. So the basic one-to-one network. The one-to-one network is not a recurrent network at all. It takes an input, it produces an output. If you gave it a sequence of inputs, it's going to analyze each input individually and it's going to produce an output for each of them. Then you had the many-to-many structure, where you got a sequence of inputs and you produced a sequence of outputs, but corresponding to each input symbol, there is an output symbol. So it's a one-to-one correspondence between the input and the output. After it has analyzed the kth input, it produces the kth output. Then we have the many-to-one. So this, for example, this is a standard MLP. This is the kind of thing that you would be doing, for instance, if you were trying to predict the stock market. You're making predictions every single day for what you must do with your portfolio. And then you can have structures of this kind, where you analyze an entire series of inputs and then produce an output. So this, for example, one example of this kind of processing is if you were performing, say, question answering. You listen to the entire question, then you produce an answer. Or if you're doing speech recognition, you watch the entire audio input and then say, this was the word hello, or this is the word Alexa, right? And then this is the order synchronous version of this one. Observe that this simply looks like many concatenations of this basic guy. And what is key over here is that you get a sequence of outputs in response to a sequence of inputs. And what I mean by order synchronous is that if you stop the inputs at this point, these two would be the outputs. But if I continued the inputs all the way to here, these three would be the outputs. So there's a order correspondence between the input and the output. But what is absent is the one-to-one correspondence between the input and the output. I have many inputs here. The number of outputs is smaller than the number of inputs. So you also have this problem of deciding when the outputs must occur. So it's order synchronous, but it's not time synchronous. See the difference, right? And then you can have additional variants, which we won't get into in the next couple of classes, except maybe this one a little bit, which we will cover today. So here you analyze an entire sequence of inputs and then produce the entire sequence of outputs. Or you can have a single input and produce an entire sequence. So the code example that we saw is where we saw a small number of inputs and then the network produced the entire code. So let's look at these things in a little more detail. This simple one-to-one correspondence. This is a one-to-one network, just a regular MLP. And here, if I have a sequence of inputs, the entire process is quite trivial. So here, you have a sequence of inputs. Each input is going to be individually processed. And from each input, you will get an output. So why am I calling this? Why do I include this in a lecture on recurrent networks when we've seen this before many times? And this is just a straightforward MLP. Here's why. It's about how you actually learn the parameters of the network. If you assumed that you have a target output for each input and you have the actual output for each input, then during learning, you can think of this entire collection as just a batch of inputs. On the other hand, if you thought of the entire thing as still processing a sequence of inputs where each input is individually being processed, nevertheless what is being produced is an output sequence, then the divergence that I define is no longer between individual elements in the input and the divergence I define is not just for individual elements, but the divergence is between the sequence of outputs and the sequence of target outputs. So you see the difference between the two? It's in the definition of the divergence. And now, if I want to train the network, so what happened over here is that the output at time t is not a function of the input at any other time or the output at any other time. So the output at each time depends only on that time. So there's a one-to-one correspondence between output and the target outputs and actual output, but the divergence still can be computed over the entire sequence. And so when you want to perform training, what you would want to do is to take the derivative of this sequence level divergence with respect to each of these outputs in order to be able to backpropagate them. This is where, and in fact, the most generic case of analyzing time series data with one-to-one networks is going to be just this one. But nevertheless, what we will often do is to sort of decompose it and say, we're going to think of this global divergence as a weighted combination of divergence at individual instance. And this sort of collapses this to the standard MLP structure. And once you do that, then the derivative of this divergence with respect to any individual output is simply going to be the weight assigned to that output times the derivative of the local divergence for that particular time instant, which is the divergence between the actual output at that time and the target output at that time. So this is really a simplification and assumption that we are making. And this kind of makes things simple to work with. But you really want to be thinking of the process as trying to compute the derivative of the divergence between two strings and the individual outputs. Right? Now, typically we'll set the weights to 0. So this sort of, the weights to 1. So this makes the backpropagation much simpler. But then again, you could change this, you could change this assumption and you'd get some interesting behaviors. And once you decide that what you're really going to do is to be summing up the individual divergences at each time instant, then the obvious divergence that you would use in the classification scenario is simply going to be the cross entropy between the actual output and the target output. Easy enough, right? Now, let's look at this guy. So we started with this, and we sort of said this is, you don't, even though it's a one-to-one and it looks like an MLP, it really doesn't have to be an MLP. Once you think of it as producing sequences of outputs and you define divergences between sequences and sequences, then the training paradigm changes. But then for simplification, I went right back and broke it back down to a simple collection of MLPs. Where is that? I have no idea. What's happening? What's happening?
Does it put anything with your laptop?
Oh, no, that's my Skype.
Oh, okay.
I'm sorry. Hi, someone's trying to Skype me. My apologies. All right. So now let's switch to the many-to-many scenario, right? When I switch to the many-to-many scenario, I'm going to actually briefly detour into modeling language. I may not actually finish this lecture today. If I don't, then we're just going to continue this on to Friday, so just be warned. Now here you have a sequence of inputs. So let's think of a scenario where you have a many-to-many network relationship where in response to each input you must produce an output. Now, although I'm showing you a left to right network over here, in practice you would really be looking at trying to do this bidirectionally, because very often the future tells you something about what you must output at the current time. But here's an example, like part of speech tagging for text. You have this sequence of words, two roads diverged in a yellow word. And for each of these words, you want to output a part of speech tag. So you want to be able to look at this and say 2 is a number, roads is a noun, diverged is a noun, and A is a determiner, yellow is an adjective, wood is a noun, in is what is it? Right. I forget what I wanted. So, but the point is, there's a one-to-one correspondence between the inputs and the outputs, and so you want to analyze the input and assign an output to each of these guys, but observe that what you assign to any one of these guys actually also depends on what you're assigning to the other. So there is this recurrent relationship, and the model captures it. So so the way you would do it, you'd process the input left to right and produce outputs after each time. Or you could do this bidirectionally, right? You can process the input left to right, also process it right to left, combine both their hidden representations to assign the actual output value at each time. Both of these are perfectly feasible. And in fact, if you were doing part of speech tagging, this is the bidirectional structure. Makes a lot more sense than the unidirectional structure, because knowing what follows will tell you something about what part of speech tag to assign to any given word. But for the rest of the lecture, I'm not actually going to be considering bidirectional structures. I'm assuming unidirectional structure. Again, as I said, this is easily generalized, right? So in this case, how do you train the network? You're going to be given a collection of sequences. No longer are you being given a collection of vector inputs. When I speak of a training instance, the training instance has a pair, which is the input and the target output. But the input is actually a sequence of vectors. The output also is a sequence of either vectors or scalars, depending on what kind of output you perform, what kind of prediction you're performing. If you're performing classification, the output would be a sequence of one-hot vectors. And so now, for each training input, during the forward pass, you're going to pass the entire data sequence through the network, generate outputs. During the backward pass, you're going to compute gradients using this divergence that you define between the sequence of outputs and the sequence of target outputs, and you backpropagate the gradient all the way through the network. Again, this is not just the sum of the divergences at individual times, unless you explicitly define it that way. This is going to be some abstract function that you define between two sequences, right? So if you were performing a backpropagation, what is the very first thing you would do? Depending on how you define the divergence function, the first thing you would need is the derivative or the gradient of the divergence with respect to each of these outputs. And once you have the gradient of the divergence with respect to the outputs, the rest of backpropagation follows exactly as before. So here, for example, you'd go down here, multiplied by the Jacobian of this box, so you'd go down here, then multiplied by the weights, go down here. We saw the whole process earlier, right? And things would aggregate as you went backwards. The key component in all of this is going to be the definition of the divergence. What is this divergence? Now, we're going to look at some simple examples of divergence in the next, for now, but these things can get fairly complex. And it turns out that if you end up with non-differentiable error functions that you want to convert to divergences, then the problem actually becomes fairly difficult. In fact, I won't go cover that in class simply because it's maybe beyond the depth required for this particular intro class, but it's an interesting topic. So one of the simplest assumptions you can make, even in this setting, is to assume that the divergence between the sequence of desired outputs and the sequence of actual outputs is simply the sum over all of these instances of a local divergence computed between the local target output and the local actual output. Now this is a simplification. This is an assumption that you're making. And having something of this kind means that now if I want to compute the derivative of the global divergence with respect to, say, this output, it's sufficient for me to compute the derivative of this local divergence with respect to this output, because the global divergence is simply looked at being viewed as the sum of the local divergences at each time. And now this becomes simple, right? So, and a typical divergence for classification problems, when you think of it in terms of a sequence of local divergences, is again the cross entropy between the target output and the actual output. Now, so here's a simple example. We're going to spend a little time on this particular problem and particularly look at analyzing text and language models for the next few minutes. So think of a model that can try to predict the next character given a sequence of characters, or maybe try to predict the next word given a sequence of words. So after observing the inputs W0 through Wk, it must predict Wk plus 1. How would we do it? So this is a nice little example from Andrei Karpathy. I picked it from his webpage. This is here, for example, this network has to look at a sequence of characters and predict the next character. So it would look at H, and it must figure out that the next word is E. Then if I give it HE, it looks at HE, and it must figure out that the next word is L. Then it looks at HEL, it must figure out that the next character is again L. It looks at HELL, it must figure out that the next character is O. It's trying to spell or predict the word hello. So in this, I'm speaking of characters, I'm speaking of giving it an input of characters, character sequences, and predicting characters. Characters are not numbers. We know that networks don't work with abstract symbols. They really need to be working with numbers. So what is the very first thing that we would do? We're going to have to predict, we're going to have to convert all of these to one-hot vectors. So for example, let's say I have only 4 characters in my alphabet. Then the 4 characters would be H, E, L, and O. No, E, H, L, O. The figure is wrong. So if I arranged my characters in alphabetical order, then they're going to be E, H, L, and O. Then the very first input, H, is going to be what? 0, 1, 0, 0. That's the character H, right? So I've seen the character H. What does it predict after seeing the character H? How does it predict the character L, E? Now, in order to predict the character E, what you really want the system to predict after seeing this input is it goes into whatever box, and out must come, that's E, H, L, and O. You want a 1 over here and 3 zeros. So this uniquely tells me that the next word must be an E. Next character must be an E. Now this is not what it's actually going to produce. What do the classification networks produce? Typically we use a sigmoid at the output, a softmax, and it produces what? A probability distribution, right? So now when it produces a probability distribution, what you really want for this guy to do is to maybe produce something like this, where the probability of E is high and the rest of them are lower than E, so that if you pick the most probable character, then that most probable character is E. So now from here, the next input, that's the character E, and the character E has the one-hot representation 1, 0, 0, 0, according to our lexical arrangement of the characters. So having done this, having fed this to the network, you want the output at the next time to be small for E and H, large for L, and small for O, right? So basically this is the kind of behavior you really want from the network. Again, the point is you're feeding it one-hot representations. The output is a probability distribution over the symbols, right? And must ideally peak at the right output. So if I were trying to do this to predict language, to predict words or characters, then the input is going to be a sequence of symbols represented as one-hot vectors, and the output is going to be a probability distribution over the symbols. So if I'm going left to right, then after having seen the characters or the inputs W0 through WT minus 1, what it predicts next is a probability distribution where if for each symbol in the vocabulary, it is predicting, it's assigning a probability. So here, for example, after seeing these two inputs, it's assigning different probabilities for E, H, L, and O. So the output is going to be a probability distribution between over the set of symbols. Now, if I use a simple cross-entropy divergence between the target output and the desired output, then what you would find is, let's say the output is the desired output is, say, y, then the target output is going to be 0, 0, 1, 0. The desired output is going to be y1. The actual output is going to be y1, y2, y3, and y4. And so we would be doing di log yi summation over all I, right? So for this term, it's going to be log of y4 times 0. It disappears. For this term, it's log of y1 times 0, so that too disappears. So also this term disappears. The only term that remains is this guy, which is going to be minus log y3 in our particular example, right? So more generally, what you're going to find is that, Akash, you look puzzled?
No, I got it.
Okay. So more generally, all you're going to do is at each time, the cross entropy is simply going to be the negative of the log of the probability that has been assigned to the target output. And the overall divergence is going to be the sum of this term over all time. Right? And this is basically what we're going to use as our divergence to train the network. So a brief detour into language models. What we really saw when I began trying to model text, look at a sequence of text and predict the next word, was an instance of modeling language. So we're looking at modeling language using time synchronous nets, or I can generalize this to generally trying to analyze language. So we'll spend a few minutes looking at language models and embeddings. It's an important topic. I'm not spending quite enough time on it. Hopefully we have a guest lecture by Graham which covers some of these. And hopefully we also have a recitation on the topic. But now consider this, right? Let's go back to the first example that we saw in the very beginning of the series on recurrent neural networks. We saw this example of what looked like a perfectly valid program that had been produced by a recurrent neural network. Now let's look at a different problem. Let's look at, I'll relate the two, right? Given a sequence of words, 4 score and 7 years, if I ask you to predict the next word, pretty much anybody who's familiar with American history is going to say the word is a go, right? Or if I give you ABRAHAMLINCOL and I ask you to predict the next character, almost certainly you're going to give me N as the next character. So there's a very definite predictability of the next character or the next word based on the past. So this is the modeling language. Now, where did these predictions come from? That's because you're familiar with language. You're familiar with history in this particular case, but more importantly, there's the language aspect of it. And what you're really doing is making language predictions. So modeling language is all about trying to make these, come up with modeling structures which can make predictions about language in this manner. The basic formula is going to be something like this. You represent the words as one hot vectors. You pre-specify a vocabulary of n words in some fixed order. Like here, we used characters and we ordered them lexically. And you're going to represent each word by an n-dimensional vector with n minus 1 zeros and a single one. We're familiar with this, the standard one-hot representation. If you were working with characters instead of language, the words, the problem with words is the number of words in a language can be arbitrarily large. If you were working with Russian, then a vocabulary of 400,000 words is not at all unusual. If you were working with English, you're still going to need a vocabulary of about 100,000 words to cover enough of the language that you can model most of what you're going to encounter. So the vocabulary can get very large. On the other hand, if you're looking at things at a character level, 100 symbols can cover pretty much all of the characters you're going to encounter in your day-to-day life if you're trying to write English. This includes numbers, periods, semicolons, spaces, tabs, the whole lot. So in this case, if you're modeling characters, your one-hot representation is going to have only 100 components. If you're representing words, the one-hot representation is going to be, for English, 100,000 components. And now, when you're predicting words, what would you do? You can think of the predictor, the language modeler, as looking at the past n-1 words and making a prediction about the nth word. So if I were to draw this as a figure, you have some box F, which is the prediction model. It's looking at the past n-1 words, and it's predicting the nth word. But then these words must be represented in some manner. And so the way we represent it as each of these words is going to be represented as a one-hot vector. And the output is also going to be not necessarily a one-hot vector. It could be a probability distribution over the vocabulary. But the ideal output is going to be a one-hot vector, right? So what is the problem over here? I just spoke of the vocabulary of English. It's 100,000 words. So what is the dimensionality of the one-hot vector? Anyone? It's 100,000 dimensions, right? Now, what volume of the 100, so what is the dimensionality of the space that these vectors live in? 100,000. Even if I'm working with characters, what is the dimensionality of the space the characters live in? 100 dimensional. Now, if I were to consider a unit cube in a 100 dimensional space, how many corners does this unit cube have? 2 raised to 100, right? Because for every, and meaning even if you are thinking of all of your words as living on a unit cube, you have 2 raised to 100, or that's approximately 10 raised to 10, which is 10 billion corners. And of these 10 billion possible corners, how many are you occupying with your characters? 100, right? Because 100 dimensions. So basically, if you think of this in terms of volume, what volume of your space is your entire collection of possible inputs occupying? Anyone? It's 0. And why is that? If I were to just look at my inputs and my input vectors, think of this one-hot representation, 0, 1, 0, 0. You know exactly what 0, 1, 0, 0 represents. It represents the character H, right? Can you tell me what this guy represents? 0, 1.000000001, 0, 0. What does this vector represent? Anyone? It doesn't represent anything, right? It doesn't matter what the extra bits you add after 1 are. It doesn't matter how small the epsilon is. It represents nothing. There is no meaning to it. The total volume occupied by that point is 0. The total volume occupied by all of your training data is 0, right? So given this, so fine. We've come to the fact that we're using these immensely large high-dimensional spaces, and yet we are occupying exactly 0 volume in this space. Does that even begin to make sense? Does anything make sense? Do distances make sense? Do directions make sense? Do point make sense? None of that makes sense. Because you know that if you go just a little wiggle off from wherever you started, you're off into nowhere land, no man's land, nowhere land, right? So let's just concede that, okay, we're willing to live with occupying 0 volume. How about the density? So if I look at a unit cube of side R, then the total density of points, the size of the cube is R raised to n, the number of points I'm using, I'm actually using in that space is just n. So for example, over here, 0, 0, 1, 0 means something, or 0, 1, 0, 0 means something, but 0, 1, 1, 0 doesn't mean anything at all, right? So I'm still at the corners of the cube, but most of my corners, basically all of my corners are not being used. If I'm living in a 100,000 dimensional space of the r raised to 100,000, I'm using in the r raised to volume of r raised to 100,000, I have exactly 100,000 points. The density is effectively 0, right? So if we are making such an inefficient use of the space, why do we use one-hot vectors? Anyone?
It makes sense to people.
Does it?
More than like real long float numbers.
Not quite, and we'll see why. Anybody else? So think of it from the perspective of a computer. Is the word, floxy, nos, nihilipilification any different from the word the? The computer doesn't have language. It's just a symbol, right? One symbol is not more important than the next symbol. What is the length of every single one-hot vector that you're using? 1. What is the distance between any two one-hot vectors? Square root of 2, right? So basically, you're coming up with a semantic agnostic representation. You're not assigning, and the one-hot representation is the only way you have of not assigning a relative importance to words going in, or a relative importance to symbols going in. It's also the only way we have, or one of the few ways we have, of actually ensuring that the distance between any two words is the same, regardless of what the words are. So you are not imposing any notion of closeness or distance on the language, right? The representation, now if you used anything other than one-hot representations, then you would have to make sure that the values you assign, the vectors you assign to each of your symbols were such that the distances between these vectors actually made sense. How do you come up with that? That's a very subjective thing if you want to do this on your own. So you don't do it. You just say everything is exactly the same. All 2 points, the distance between any 2 points is the same as the distance between any other 2 points. Every vector is exactly the same as every other vector. But the problem with this is that although you make no assumptions about the relationships between words or about the actual relative importance of words, the usage of the space is horrible. So what we would like to do is project all of our points into a lower dimensional subspace. Now when you project everything down to a lower dimensional subspace, the total volume used is still 0 because each point still becomes just a point. So the projection of 1.000001 still doesn't mean anything. You're not really improving on the volume property of the space, but you are improving in terms of the density of points. But now the problem becomes, what is this projection, what is this hyperplane that I must project it on such that everything makes sense, that the positions, or if not the positions, at least the distances between points make sense. So we're going to learn this plane. And if you learn this plane properly, the distances between projected points should ideally capture semantic relations, or if you learn this from analysis of language, then your projections should be such that the geometric arrangement of all of your words on this projected plane actually has some semantic meaning to it. So here's how we're going to do it. I'm going to assume that I'm going to take these one-hot vectors and project it onto some plane. And the projection is going to be done with some matrix P. Now we know that the projection is just a linear operation. I just take my vector, I multiply it by B, I get a projected version of the vector, right? And so to predict the next word, instead of looking at the words themselves, I'm going to look at projected versions of the words. So here is the same figure that I had earlier, except that instead of working directly off the one-hot vectors, it's going to work off the projected versions of the one-hot vectors, right? And this projection is going to take this n-dimensional vector and zap it down to some m-dimensional space. So the projection is going to be an m cross n matrix. And we're going to use learn p. So as a result, p times w is going to be an m-dimensional vector. And you're going to learn the matrix p using an appropriate objective. Now, how do you do it? In the new neural network context, it turns out it's actually very simple. Now, think of it this way. I'm going to start off with an n-dimensional vector. I'm going to multiply it by an m cross n matrix, and I'm going to end up with a m-dimensional vector. But then one way to look at it is that there is an n-dimensional input and a m-dimensional output, and each output is obtained as a linear combination of the m inputs and inputs, right? So I can think of this entire matrix operation, and we've seen this before, so this is not surprising, right? As just a simple one-layer network with a linear activation. So once I do that, this entire operation over here, in this entire operation over here, all of these projections become one-layer networks with linear activation, with one extra constraint that this network is identical to this network is identical to this network. So all of those networks are shared parameter networks. And we know exactly how to deal with shared parameter networks, right? So now all we will do is to use this entire structure to learn our both the ability to predict and our projections. So here's one of the early papers by Benjy et al. In 2003, where they were using a time delay neural network to predict the next word. They were looking at the past, and in this example, they're looking at the past 4 words. Each of the 4 words is projected down, and it's passed through a recurrent through an MLP to predict the 5th word. Then they take W2 through W5 and predict W6. This dotted line over here is just to indicate that in their paper, they actually had direct connections from the output of these to the output to this orange box as well, but that's kind of irrelevant. But here's the basic structure, that you can really simply use a time delay neural network that looks at the past k words to predict the next word. The one distinction being that you're first going to pass all of these words over here through the projection. Now observe that at the output is still one hot. You're trying to predict the next word, and you're going to be using the same structure as we had over here. The only thing that happened is that at the input, you went from this uninformative n-dimensional space to some lower dimensional space where maybe the arrangement actually made sense, and then use those representations to actually learn the language. You can have other variants. So this is the so-called soft bag of words, where if you want to predict the word W4, you look at all of the words on either side. All of them are projected down to this lower dimensional space. And then instead of using them independently, you just do some kind of a mean pooling, and then you get a single vector that you use to make the prediction. So what this means is that here, the order, the arrangement of the words at the lower level doesn't really matter, although it does become insensitive to the number of words that you're using to make the prediction. So these are just models that have been proposed. Or here's the alternate model, where you use W7 to predict all the words on either side. So you'll be using each word to predict the past 3 words and the next 3 words, or the past 5 words and the next 5 words, and so on. So these are called skipgrams. This is a soft bag of words. They are the variants. hopefully we'll cover these in a future recitation, but I was just trying to convey the idea of projecting things down and computing so-called word embeddings or character embeddings. Yes. Go ahead.
I'm wondering, so we use the embedding in the inputs, but why not reusing the output?
How do you represent it, right? So when the point is, if you're looking at the embedding in the output, what do you mean by predicting a real valued vector? Remember, the L2 distance doesn't make sense. The projection of 0, 1, 0, 0 makes sense. The projection of 0, 1.000000001 doesn't make sense. So there's no, so having an L2 distance based error is, although it's kind of differentiable, is not an informative, in the linguistic sense, it's not informative, right? Yeah, I mean, look at this. Let's go back here. We saw this, right? I mean, why do I need to have, even over here, why do I need a KL divergence? Can I use an L2 divergence?
Okay, I mean before that we would have P.
So if you put a P over here, that's P going in, right? So the flow of information is left to right, okay? So if the flow of information is left to right, then what is output? Are you making a prediction of the projection, or are you making a prediction of the word itself? If you're making a prediction of the projection of the word, how do you quantify the error? If you're quantifying the error in a cross entropy sense, then the projection becomes irrelevant. If you're quantifying the error in an L2 divergence sense, L2 divergence doesn't make sense.
Okay.
Right?
Yeah.
See the point? Yeah. But what they do find are that these projections are really kind of cool. You find, for example, that after you project things down into this lower dimensional space, the distances between vectors carry information. So, for example, the vector that translates China to Beijing is essentially the same vector that translates Russia to Moscow. So if you take this dotted line and you add it to China, you're going to end up at Beijing. The same dotted line, if you add it to Russia, you're going to end up at Moscow. So that vector seems to capture the concept of capital of. Or you have these other things where you can say man plus correction equals woman. You take the same correction, you apply it to a king, you get a queen. So they actually, if you learn these things properly in the embedding space, the vectors seem to make sense. Again, this is cherry picked. When people show you these examples, they show that you actually learn something meaningful. It doesn't mean you can actually use those relationships. Like I said, the embedding of 1.00001 is not a meaningful embedding, right? But this is some kind of post facto analysis. Anyway, so if I want to train a language model, how do I do it? Using a recurrent network. I just have the recurrent network as before. I'm going to use 4 words, and I'm going to try to predict the 5th word. I'm going to use the first k words, and I'm going to try to predict the k plus 1th word. And so here from W1 I predict W2, here from W1 and W2 I predict W3, here from W1 through W9 I predict W10, and so on. Each of these words is actually zapped down using a projection matrix. This could be an entire LSTM structure. It could be unidirectional or bidirectional. The whole thing can be trained from using backpropagation with a lot of text. So now, if I want to make one of the things I can do with this model is make predictions. So remember, what the model is really doing is it's taking a bunch of inputs. It's computing a probability distribution over the next symbol in this case. So here I could, for example, give it the first, after having trained the model, I could give it the first 3 words. After having seen the first 3 words, can somebody tap her? She's asleep. Okay. After having seen, do you want to go wash your face?
No, I was seeing a question.
Okay. So after having seen the first 3 words, if you want to predict the 4th word, what you're really going to get is a probability distribution over words in the fourth position, right? From those so you're going to get a probability distribution of this kind. And you could just pick the most likely word and call it the next word. And so once you call that the next word, it's like saying I've seen W1, W2, and W3, and I've seen W4, although W4 really was what I chose from my prediction at the previous time. And now using this input, I can go back and predict the probability distribution for the fifth word, which would be something of this kind again. I can pick yes.
Are the predictions one-hot encoding, or are they?
No, it's a probability distribution. It's choosing from it, right? That's what he said, that I'm going to get, the output is always going to be a probability distribution. I can pick the most likely.
And then what do you feed back into the network?
So let's say I give you 4 score and, then you're going to get a probability distribution over all the words in the dictionary. And if you're lucky, and if you learn the Gettysburg Address, the probability for the word 7 is greater than the probability for any other word. So if you pick the most likely word, you're going to pick 7.
Yeah.
Right? So at the next instant, you're going to pretend that 7 really was what you saw. And so now you're going to have 4 score and 7. And then that goes through the network, and it's going to give you a probability distribution of all the words. And if you're lucky, then the probability for the word years is going to be higher than the probability for everything else. Then you pick years. Then you feed back into the next.
Is the embedding of years passed back in, or is it the?
So it's the word, right? So it's the word, but then look at what happens over here. The word goes in, but here you're going to embed it, right?
Oh, embedded.
The input is always the embedded version, but what you're getting back is what you must treat as the next input. Yeah.
So there was a sentence mentioned in one of the previous slides which said that we may not know always when to exactly give the output.
So that in this particular case, no. Okay, we haven't gotten to that problem yet. Here we are just saying that I'm seeing the past n words, I'm going to predict the next word, right? Okay, so I'm running out of time really fast, but that's okay. So you get the idea of how this is produced, right? Very simple, very straightforward. That I would take the first 3 words. So I'm going to get something like this. I would, where is the chalk here? So I'm going to have 4 score and, so this goes through my network, doesn't matter, I ignore this one out over here. This goes in, I ignore this guy. This goes in, and over here I'm going to get a probability distribution over all words. So I pick, this is the highest, so I can pick this one. This ends up being, say, 7. So I'm going to say the next word is 7, which is this one, same thing here, right? And then that goes in, and I'm going to get a probability distribution over words once again. And this is the highest. This doesn't have to be a go. It could have been, before, right? And if this were before, then the next word I would treat, which is wrong, and then go on to make my next prediction. Yeah? Right? So what happened over here? This was a recurrent neural network that was trained on character level prediction. This is a character level model trained on all of the Linux source code. And then it was used in this mode where they gave it the first, maybe I'm not sure exactly how much they gave, and then they let it run in generative mode. And observe what it does. It actually gets comments, it closes the comments, it knows how to open a function, it knows that functions have arguments which must be bracketed by parentheses, it knows that functions must be started with a curly brace, then things are written, curly braces must be closed. It produces the whole thing. It produces the entire program. Pretty impressive, right? Or here's an even nicer example from this website, where they trained this on a bunch of music, and then they gave it the first few bars of a piano and just produced it, and was a MIDI. It sounds totally authentic, doesn't it? It's a perfectly reasonable. This is by a recurrent neural network. It's pretty impressive. So, now, questions? Yeah, so I'm going to return to our problem, right? So returning to our problem, we are going to be talking about defining divergences in other scenarios. We have just a few minutes. I'm going to maybe go over a few minutes. Let's consider this problem where I'm trying to perform sequence classification. You're classifying a full input sequence, and like say phoneme recognition. I give you a sequence of vectors. You have to give me the output. Tell me which phoneme it was. Or I give you a sequence of words which represents a question, and then when you're done seeing the entire question, you have to answer. Color of sky, blue, right? So question answering system. You see the input sequence, and the output is answered at the end of the question. So question answering, phoneme recognition, same problem, right? Now observe what's happening over here. When I construct a network of this kind, do you magically just construct a network that only produces an output at the end of the sequence? Not really, right? What is really happening is that it's considering the entire input, but it's only producing an output once you have decided that the input is complete. My question is over, produce an output. It's not as if the network automatically knows when the question ended. You stopped it, and then you're going to read the output, right? Make sense to you? Right? So in this setting. What this means is that you're actually also producing outputs out here, you're just ignoring them. This is exactly what happened when I was doing 4 and 7 years ago, right? I ignored these first two guys. So you're actually producing outputs everywhere. You're only considering the output at the final time. Clear? Right? So now if I'm training this network, I'm training a question answering system, or I'm training a phoneme recognition system, what do? I'm going to have input-output pairs, so I'd have a sequence of input vectors. At the end of the sequence, I have a target output. So the way I would do the training is I'm going to pass it the sequence of inputs. I get the output at the end of the sequence. I can compute the divergence at the end of the sequence. I can backpropagate this divergence, and I can learn all of my parameters, right? And this divergence must propagate through the net to update all parameters. What is the problem? If the input is very long, basically you're going to run into vanishing and exploding gradient problems anyways, right? So also, the total amount of feedback you're providing is just one per entire sequence. That's basically because you're pretending there's nothing useful that came out of these locations. You're throwing them away. But what you could do instead is to say that if this sequence of, say, speech vectors represents the sound R, it was R everywhere, right? So I can pretend that the intermediate responses must also be the symbol R. And once I may pretend so, then I can actually define a divergence between sequences, which here the intuitively most appropriate one is to use basically the same divergence that you used out here at each of these points and sum them up, except you want to have weights. Maybe as you go past into the past, you consider assign lesser and lesser importance to the divergence as you go back into the past, right? And so this doesn't now it's kind of what must be these weights be? If you're doing speech recognition, having weights of 1 kind of makes sense. If it's the sound R, it's the sound R everywhere. On the other hand, if you're doing a question answering system, it's kind of stupid to say the answer must be blue as soon as you see the word color, or that the answer must be blue as soon as you see the word color off. It's only when the word sky came in that the answer blue made sense. So in this case, the obvious setting of these weights is 1 over here and 0 elsewhere. But the generic setting is this weighted cross entropy if you're performing classification, or it could be L2 if you're doing anything else. and this is the divergence that you would actually use when you're training. So we've seen how to deal with this particular problem. We know how to do the inference, we know how to do the training, right? The next one, I'll stop right here, we'll cover this in the next class, but here is a much more challenging problem where this is the order synchronous, time asynchronous sequence to sequence prediction. So here, for example, I'm getting lots of speech, and each time one phoneme ends, I want to produce an output. And say this was the word, this was the phoneme ah, this was the phoneme this was the phoneme d, right? The problem is, all you're seeing is the sequence of inputs. You don't really know when you must be producing these outputs because you don't know beforehand when each of these phonemes ended. So you have orders you know that you must be getting a sequence of outputs. The exact location of the outputs is unknown beforehand, and determining these is also part of the bigger problem, right? So we'll look at this in the next class. Questions? Thank you.